Alright, this is the second video, so it's going to be quicker than the first one. I would still recommend that you pause and see how far you can get before you have to kind of like tag in for some help. So this one's going to be a lot quicker. If you have questions here, just go back and watch video 1, or watch video 1 first. If you're just watching this one first, watch the one that says like first video. So we have this function, again, random function that I just pulled off from online. First thing we want to do is factor. So in the top I can pull out a 3x, and I'm going to be left with x. So sorry, some technical difficulties there. And then in the bottom, I can factor this into x minus 3, x plus 1. All right, so next thing we want to do is find the domain. All right, so the domain is going to be where the denominator is equal to 0. So we're going to get x is 3 and x is equal to negative 1. And we got those by setting x minus 3 equal to 0, x plus 1 equal to 0. So our domain, all real numbers except for negative 1 and 3. All right, so in this case, nothing factors out. So our simplified version is 3x times x minus 4 divided by x minus 3, x plus 1. Since none of those factors canceled out, there's no holes. Right, we only would have gotten a hole if something in the top and the bottom would have canceled. Right, so our vertical asymptotes are going to be both of these values. Right, they're the only things that are left that we can't have in our domain. So x is equal to negative 1, x is equal to 3. So negative 1, 1, 2, 3. It's going to have some vertical asymptotes there. All right, x equals negative 1, x equals 3. All right, so x-intercepts are going to occur when the numerator is equal to 0. So we want to set the top equal to 0. So 3x times x minus 4 is equal to 0 when 3x is equal to 0, or x is equal to 0, and when x minus 4 is equal to 0, or when x is equal to 4. So we have two x-intercepts. 0, 0, the origin. Whenever the origin is an x-intercept, it's also the only y-intercept. There can only be one y-intercept. And we also have 4, 0. So we have an x-intercept of the origin, and we have an x-intercept over here at 4. All right, so we have, let's see, for horizontal asymptotes, we want to just look at the ratio, or first off, we want to find the degrees. Again, doesn't matter which one we use. So I tend to look at just the original function, but it doesn't matter if you use this one or the simplified one. So the degree of the top is 2. The degree of the bottom is also 2. So this is the case where the degree of the top and the degree of the bottom are equal. So in these cases, we're just going to take the ratio of the leading coefficients. And again, just as a quick reason why we do that, all we care about is long-term behavior. So long term, the only thing that kind of like lives on in the numerator is 3x squared. The only thing that lives on in the denominator is x squared. When we cancel these things, we get 3. So this means we have a horizontal asymptote of 3. So that should be a little bit more kind of like math technical. A horizontal asymptote is y equals 3. All right, so we actually know some sneaky things about this function, but I'm not going to write the sneaky things yet. We want to just finish off what we have. So let's make a table of signs. Remember, we only care about vertical asymptotes and zeros. So negative 1, 0, 3, and 4. Those are the parts of the domain. Using this simplified version of the function, remember, that's going to be this one here. All we care about is what are the signs, not what are the actual values. All right, so I'm going to pick some number less than negative 1. I'm going to think negative 2. So if I have 3x, 3 times negative 2 is negative. X minus 4, negative 2 minus 4 is also negative. Negative 2 minus 3 is negative. And negative 2 plus 1 is also negative. So on this interval, it's positive. And I'll explain how we actually knew that in a moment. If we pick some number between negative 1 and 0, aka negative 1/2, so negative 1/2, When you plug that into the simplified version, 3 times negative a half, 3 times a negative is negative. Negative half minus 4 is negative. Negative a half minus 3 is also negative. Negative a half plus 1 is positive. Ooh, so it's negative on this part of the interval. If I plug in something between 0 and 3, like I'm thinking 1, 3 times 1 is positive. 1 minus 4 is negative. 1 minus 3 is negative. And 1 plus 1 is positive. So I have 2 negatives, so my function is positive. And finally, or nope, not finally. So if I pick something between 3 and 4, like 3.5, 3 times 3.5 is positive. 3.5 minus 4 is negative. 3.5 minus 3 is positive. 3.5 plus 1 is positive. There's only one negative, so it's negative on that interval. And then finally, if I pick some number greater than 4, like 5, when I pick 5, 3 times 5 is positive. 5 minus 4 is positive. 5 minus 3 is positive. 5 plus 1 is positive. So it's positive on this interval here. So we can fill in what our function looks like. From negative infinity to 0, it's positive. It has to approach its asymptotes. So it's going to do something like that. So that's this part of the domain. From negative 1 to 0, it's negative. It has to approach its asymptote, hit this 0. From 0, so that's this part. From 0 to 3, it's positive. So it has to go off and go towards its asymptote. Remember, it can cross a horizontal asymptote in the middle. It just can't cross a horizontal asymptote on these kind of like end intervals. From negative 3 to 4, the function is negative. So it has to start here by its asymptote, hit, and then from 4 to infinity, it's positive. It has to go off and approach this horizontal asymptote. So it has to look something like that. Again, this was a quicker video. I'll do a couple more of these quicker ones. Hopefully I can get them down to about 5 minutes because nobody probably wants to watch an hour worth of rational function videos. Most of you probably don't want to watch an hour's worth of rational function videos.